on the reals. And what that means is that if we calculate the Taylor series, so that the Taylor series, so the nth Taylor, this is what? Right, and then, so it'll be the nth Taylor polynomial. Now here, we have to, our job here is to show that Rn of x, which would be what? I mean, technically it is, oh man, I am sorry, I'm drifting. A little dizzy today. I don't know what's going on this year. Where'd that go? Trying to find his definition. I want to say f of x minus, yeah, fine, that's what I want to say. I'll say it. So this would be f of x minus Tn of x. And so to show it's analytic, I need to be able to show that as n goes to infinity, I get what? We need Rn of x to go to 0 for all x in the reals. That's your goal, is to show that the remainder term goes to 0 for any x. So to do this, you have to apply the Lagrange's form of the remainder in a kind of sneaky way. All right? What does the Lagrange's form of the remainder tell us? Where was that thing? Thank you. It gave us a tool to bound the remainder according to the n plus 1 thing on the blah, 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 blah words. So Rn plus 1, right, of x is the absolute value of it, right, is less than or equal to what? The absolute value, right, x minus c to the n plus 1 divided by n plus 1 factorial, right, times what? Yeah, the fn plus 1 of z, right? So let me explain what's going on here. It's kind of complicated. There's a lot going on here. So you got a center, C, right? And you've got x, let's suppose, you got x here. Let me say x is positive just for the sake of me not going nuts. Here you got x plus c. You got c plus x over here. All right? And over here you got c minus x. Fine. If you want me to be careful, absolute value x there. Happy? So this is the, well, the z has to fit somewhere in here is the point. The theorem says there exists a z somewhere in there. All right? There exists a z somewhere in here such that this is true. Right? So the way we actually take advantage of this theorem is to say that this is less than or equal to, x minus c to the n plus 1 times m divided by n plus 1 factorial. And here what you want is a bound. You want, the I'm missing absolute values on this. You want the n plus 1 derivative at z to be less than or equal to m. We could say x. Well, I don't know, whatever you want to put in here, Pac-Man. For any Pac-Man. Well, I'm sorry, I've used up so many stupid letters. Let's say for z, and now I'm thinking of z being a variable, though. Okay, for every z in that interval, that has to hold. If I have that, then I can replace this variable z, which I don't know what it is, with that. All right. So, this function, what is the kth derivative? Or what's the nth derivative of x for the function we're considering? It is minus 2 to the n, right? E to the minus 2x. So in other words, the nth derivative evaluated at 0 is, oh, but I don't care about that. So sorry. So there it is. That's the nth derivative. So I want to bound, right? Can you figure out what I should, so if we, let's say, I want to fix, let's say fix x naught greater than 0, all right? And I'm going to consider x an element of minus x naught to x naught, okay? So my question is, can you tell me what I can bound the nth derivative of x for such x? If x is between x naught and minus x, of course, let's just take the absolute value of it. So that's equal to 2 to the n, e to the minus 2x, right? Now it depends on whether n is n is even or odd, right? If n is even, so e to the minus 2x is decreasing, but the derivative, right, minus 2 e to the minus 2x is increasing. The second derivative, 4 e to the minus 2x, is decreasing. The third derivative increasing, the fourth derivative increasing, and back and forth and back and forth. They're either increasing or decreasing everywhere. So if a function is increasing, it looks like this, right? If a function's decreasing, it looks like this. So I'm looking at this interval minus x naught to x naught. In the case it's increasing, right, what should I use as a bound? If this is an increasing function, if n is such that it's increasing, I should use this one, right? If, on the other hand, it's a decreasing function, I should use this as my bound. So, I mean, what do you want to make that? Let's see here. How to say this? Oh, wait a minute, but think I'm making this too complicated. I still have just this, right? So just focusing in on this piece right here, this is less than or equal to what? Forget about whether n is even or odd there. That's already good. That's already got killed by the absolute value anyway. What am I worrying about? This is what? If I'm in here, what can I replace? What's this smaller than? It's like this, right? So I want e to the 2x naught. Ah, curses. See, and I'm still in trouble because I need a number to make this thing really, well, I guess I mean, you can make use of this, right? Because we have Rn, I mean, maybe that's enough. Rn plus 1 of x, right, is less than or equal to, what is it? X to the n plus 1, right? Over n plus 1 factorial, 2 to the n, right? E to the 2x naught. And if you look at x, what's the biggest x can be? X to the n plus 1, what's the biggest that can be on this interval? Looks to me like we've got a 2 to the n over n plus 1 factorial. X naught to the n plus 1, e to the 2x naught, right? And if we fixed x naught, right, fix x naught, independent of n, what happens as n goes to infinity there? It goes to 0, right? Because, I mean, there's an ambiguity that you have to deal with here. We've got 2 to the n over n plus 1 factorial, but we know in the end who's going to win this fight, right? I mean, n factorial wins. N factorial beats 2 to the n eventually. Pretty fast, actually. So this goes to 0. This is, well, aha. Well, that's the other issue, right? This is troubling, right? That's x naught to the n plus 1. If x naught is big, that can be big, right? But again, that's just exponential. So if you go far enough out in the factorial, that will beat that down as well. And so this whole thing, in a nutshell, goes to 0 as n goes to infinity. Admittedly, I have left out some details. And so that shows that the remainder of n plus 1, the remainder term goes to 0 for all x between x naught and minus x naught and x, where x naught's fixed. But x naught was arbitrary, so this shows that it is analytic on the whole reals. This is the start of a careful argument. It is not the end of it. And I hope you understand now why I don't test on this topic, right? Because to actually ask students to prove that functions are analytic, in other words, that they converge to their Taylor series, is really hard. Except for one class of functions. Trigonometric functions is easy. Because trigonometric functions, you got this. Pretty much. If you have like sine of x or something, you can just, it's got no x depend. There's a natural bound for the trigonometric functions that makes this argument easier for them. But, yes. And we eventually, well anyway, that's, so. I do ask some hard homework questions. That is definitely one of them. Yeah. What's that? Do we have another day for homework tomorrow? Just one more day. So tomorrow, I am not going to answer questions about approximation, and I'm not going to answer questions about proofs, and I'm not going to answer questions about this. Tomorrow, we must focus on finding Taylor series for functions, mostly, and or first three-term kind of stuff, all right? Because today we have, it has devolved into the hardest, absolute hardest part of the homework, which is fine. We have this time, but it also, I think, can be discouraging as the test looms about. You shouldn't confuse these problems with what's on the test, right? What's on the test is more like that, or this. Not so much like that. That is, to me, very difficult. Anyway, I shut up. See you guys tomorrow. Whoa, I'm so dizzy today. Man. Whew.